Welcome to Lecture 110, Frequency Response of RC Circuits. The frequency response of RC circuits will always deal with sinusoidal voltages. The resulting voltage, drops, and currents will be a sine wave with the same frequency as the applied voltage. The current always leads the voltage by 90 degrees in an RC circuit, and a good way to remember this is to think about the word ice. When we cover the inductor, we will discover that the voltage leads the current by 90 degrees in an RL circuit, and we can use the word Eli to help remember that. In school, we use the sentence Eli the Iceman to remember this relationship. When a 90-degree right-angle relationship exists between two quantities, the quantities can be represented by a Phasor diagram as illustrated here. Here we have a resistance, just a pure resistive circuit, no reactance, and the current and voltage are in phase with different magnitudes. But in the inductor, the voltage leads the current by 90 degrees, and here's our voltage phasor and our current phasor. In the capacitor, the voltage lags by 90 degrees, and that's could be illustrated right here. This allows us to use a thing called the Pythagorean Theorem, which states that for a right angle, the hypotenuse is the square root of the sum of the squares of the other sides. And you can see this as here. This could be your phasor voltage phase or a current phase, this as well. And this would be the result of the two vectors, or your XC, which would, by Pythagorean, we have C squared equals A squared plus B squared. You want to find what the value of C, you take the square root of the A squared plus B squared. Understanding this concept gives us the ability to calculate the relationship between a voltage and current with respect to the phase angle between them. Let A be Y equal to Y, B equal to X, and C equal to H. We have the relationship now. X, it could be current or voltage, as it depends what's Eli or ice. H times the cosine of the angle equals the phasor vector value of the x component. Y equals the hypotenuse times the sine of the angle, theta, and then there's your y phasor component. Now, if you know these two components here, you can take the arc tangent of y over x, giving you the angle, the phase angle between the two vectors. Impedance of a series RC circuit. Impedance is the total opposition to sinusoidal current flow and is expressed in ohms. In a purely resistive circuit, the impedance would be zero, there's no reactance, and so the impedance is simply equal to the total resistance. In a purely capacitive circuit, the impedance is the total capacitive reactance. The impedance of a series RC circuit is determined by both the resistance and the capacitive reactance. As we can see here, this is just an R circuit, simple circuit, Z equals R. Here is a capacitive circuit, and Z equals XC. Here in an RC circuit, Z equals the square root of R squared plus XC squared. Now we'll cover how Ohm's law applies to XC. We first need to understand the relationship between the capacitive current and the voltage. Recalling that the current is the rate of flow of a charge in a circuit, reviewing that a derivative is the instantaneous rate of change of a quantity, so then I can be expressed as the instantaneous rate of change of the charge Q with respect to time. This gives us differential equation. I equals the rate of change of the charge with respect to time. Since in terms as instantaneous quantity, Q, the charge, is equal to the capacitance times the voltage, calculus tells us that the derivative Q equals dQ dt, which becomes Q equals C dV dt. Since I equals dQ dt, we get the following relationship. I equals C, of the differential of the voltage with respect to time change. But in this equation in words, it says the instantaneous capacitor current is equal to the capacitor time the instantaneous rate of change of the voltage. You can deduce that the faster the voltage across the capacitor changes, the greater the current is. And here's a Cartesian graph of the voltage lagging by 90 degrees the current. Capacitor reactance is the opposition to current flow, expressed in ohms and symbolized by XC. This reveals a property that shows an inverse relationship between XC and the capacitance and frequency. This produces a formula that allows us to calculate the value of XC. XC is inversely proportional to 1 over 2 pi FC, where XC is in ohms, F is in hertz, C is in farads. The 2 pi appears in the denominator as a constant factor. It shows the relationship of a sine wave to rotational motion. 2 pi is in radians, and our circle's in degrees, 360, but this is the radiant value of a circle of 360 degrees. We do all our calculations in electronics in radians, don't do them in degrees. It shows the relationship of sine wave to the rotational motion. Now, applying Ohm's law to XC, V equals I times XC, I equals V over XC, and XC equals the voltage over I. Where XC is used in place of R, both current and voltages must be expressed in units of RMS, peak voltage, peak-to-peak voltage, or average voltage. And we will cover each of these next. There are several ways to express the value of a sine wave in terms of voltage or current magnitude. The amplitude A is a general term referring to the amount of voltage or current for a given sine wave. The amplitude of a sine wave can be described in terms of voltage or current in several ways: instantaneous, peak, peak-to-peak, RMS, which is also referred to as effective, and average values, as you can see in the graph here. So peak to peak is from this peak to this peak. Peak is from here, from the zero crossing to here. RMS is the peak voltage times 0.707, or which is a square root of 2 over 2. And average is equal to the peak times 0.637. We'll go over each one of these now. When we will begin with an explanation of instantaneous value. The instantaneous value of a sine wave varies from one instant to the next with respect to a specific timestamp expressed by lowercase v and I. So this is v, and this is the instantaneous time stamp. And we can do that all the way through the wave. The next form of describing the sine wave value is peak value. The peak value of a sine wave is the amount of voltage or current at the positive or negative maximum points, referenced as the zero crossing. The positive peak occurs at the positive maximum, and the negative peak occurs at the negative maximum, expressed by an uppercase V or I. Peak to peak value is the voltage peak to peak, or the current I peak to peak, from the positive peak to the negative peak, as you can see illustrated in figure 5. It is also twice the peak value. So V peak to peak voltage is equal to 2 times VP. I peak to peak is equal to 2 times IP. Root mean square is represented by RMS. It refers to the mathematical process by which this value is obtained. The root mean square value is also referred to as the effective value. Most AC voltmeters measure RMS. When measuring the voltage VAC out of your wall socket, you're measuring RMS. The RMS value is the measure of the heating effect of a sine wave on the reactance. The DC value that produces the same amount of heat as the sine wave is the RMS value of that sine wave. That's very cool. So as you can see, VRMS is equal to the voltage peak times 0.707, and current RMS is equal to IP times 0.707 as well. The last way to represent these values of the sine waves is average value. This value is always measured on half cycles because a full cycle will always equal zero. Remember, it doesn't dissipate or energy, so it doesn't retain the energy when it goes to the opposite direction. So V average equals VP times 0.637, and I average equals IP times 0.637. All right, Ohm's law applies here just as it did with R. You can substitute XC for R here, or R squared plus XC squared, and the square root of that as well. Now, for peak voltages, IP equals VP over R. Peak to peak, IPP equals VPP over R. RMS, VRMS over R equals IRMS, RMS. And then I average equals V average over R. Energy in a capacitor. A charged capacitor stores energy in the electric field existing in the dielectric. Dielectrics can be mica, ceramic, paper. It can be shown that the energy stored by a capacitor is equivalent to the capacitance multiplied by the voltage square, all divided by 2, where V is the voltage across the capacitor, C is in farads, V is in volts, then the energy is in joules. The capacitor does not dissipate energy, it only stores it. Also, current doesn't flow through a capacitor, it only appears to flow. The current that appears to flow through a capacitor is called displacement current and refers to the fact that the electric field changes in time as the capacitor is being charged. This produces the effect of creating a magnetic field according to Ampere's law, just like direct current does. As this here, you can see in figure 7, the charging capacitor, the different phases of it, and how that affects the power with respect to the current and voltage. This here is a great illustration of displacement current. You have your current going into one plate of the capacitor, the electric field, the potential being created here between the two plates. Here's the other plate. And as this charges from the effects of this electric field, current flows out this side. The math behind the proof of this displacement current is beyond the scope of this lecture, but the following link is a comprehensive explanation of the concept and math involved. It's very, very good. There are 3 types of power with respect to the capacitor. The first to cover is instantaneous power. The product of V and I gives you your instantaneous power. The second type of power to cover is average power. Ideally, all the energy stored by the capacitor during the positive cycle is returned to the source during the negative cycle. Thus, no net energy is consumed in a capacitor, so average power is 0. But because of the leakage resistance in a practical circuit, a very small percentage of total energy is always dissipated. The third type of power is reactive power. The rate at which a capacitor stores or returns energy is reactive power. Reactive power is a non-zero quantity because at any instant the capacitor is taking energy from or returning energy to the source. The following equations are used to calculate the reactive power. You just have the VRMS, everything's in VMRS, and any angles and stuff like that, remember, are in radians. So that's the end of part 1 of the lecture of the frequency response of RC circuits. We're going to go into the different types of dielectrics and then the calculating of the capacitor with respect to different dielectrics. And then we're going to go into low pass, high pass, and band pass filters next. We're going to open up the QUCS and then show you how RMS value will equal a resistance value, and we're going to measure the current and voltage and calculate our powers. That's it. I hope you had fun. Okay. Instead of doing the QUCS like we had mentioned in the previous section of this video, we're going to go into the PTC Math CAD and show you how the impedance of C varies with the frequency. We're going to do four frequencies, one at 1 kilohertz, one at 10 megahertz, one at 100 megahertz, and one at 1 gigahertz. So open PTC Math CAD. I like to straighten out the paper. And we'll write a title of this, Impedance with respect to frequency. Open that, stretch that out a little bit. Now this is really actually with respect to, you'll see that a lot of times with a WRT, respect to. So first we need our frequency. So we start out at 1 kilohertz, so F1, shift colon, equals 1,000 hertz, or 1 kilohertz. Come up to the units, go down to frequency, select hertz. You have to do it like this. Next, our capacitor, C, shift colon, equals 1 nanofarad. Come over to the nanofarads, the units, capacitance, that's conductance. Capacitance nanofarad equals that. We want the frequency to be in radians, and we know that omega, little omega, equals the radian equivalent of the frequency. So to convert the frequency to radians, you take 2 times pi, come up here to the constant, get pi, times F1. And that'll be your frequency in radians. Then you say XC, semicolon, shift colon, equals the equation 1 over omega times C. Must put the operator in there. Then we come down here, we say XC equals, and there we got it. That's the impedance of the capacitance at 1 kilohertz. You see it's quite high. Let's go to 10 megahertz. So we go F2, shift colon, 10 megahertz. Down to F. So you have to differentiate between the different omegas. Otherwise, the code gets confused. So we're going to call that omega 2, 2 times pi. And actually, the guy that I studied this from and learned how to do this, F2, he would use this as a function and would pass in the different variables. Each variable had their own unique name. And that way the software would not get confused. So we're going to say X32, shift colon, 1 divided by omega 2 times C. Come down here, say XC2 equals 15.915. Now, if you don't do this and you'll solve this, this will become 15.915. And as each one you solve, the one previous, it's this software or this equation here starts using these variables. But because of this now, it will not do that. Now we're getting the correct answers. So now we're going to do 10 megahertz. Let's do 100 megahertz. You can see how the resistance went down. F3 shift colon. It's 100. Go to my units. Find the megahertz right there. C is the same. Do an omega 3. Shift colon. 2 times pi times F3 equals the radiance of the frequency. Our F3 is 100 megahertz, and then 2 pi F3 is the radiant value of that. So now we say type in XC3, shift colon, 1 divided by omega 3 times C. Say XC3 equals, and again, as you can see, the value is cut in half because our frequency has gone up by, not cut in half, but moved to decimal point because we're moving the decimal point of the frequencies. Anyway, a little bit more here in this case. So let's do 1 gigahertz now. Call it quits with that. F4 equals shift colon 1 gigahertz. Omega 4 shift equals 2 times pi times F4 bring that down. Now we're going to say, type in XC4 shift colon 1 divided by omega 4 times C equals, and then type in XC4 equals and see, I typed the small c, the software got confused, got the wrong answer. Type in the correct c, and we get the correct answer. So as XC gets smaller and smaller, of the capacitor's reactance gets smaller and smaller, it appears as a short. So if it's in a RC circuit and the capacitor, one end is to the ground and the other end is to the resistor, at 1 gigahertz, it's going to appear as 0.1 ohm, essentially ground. And that would create a low pass filter. Everything below 1 gigahertz would be pass, but gigahertz and above is going to be stop, low pass filter. High pass filter does the exact opposite. And then when you combine the two, control the pole where the 3 dB point is, you make a band pass filter. Okay, that's it. Okay, now we're going to do our QUCS. Open up QUCS. We're going to study the RC circuit that we were using in PTC Math CAD to calculate our reactance or our impedance in the RC circuit. I've already created this circuit. In the graphs, we're going to learn how to do the graphs, set up these graphs. It's just a Cartesian graph. We change the axis to semi-log, which means that the base log is a dB. You can see the different decades here. And as each one goes up by 10, that's a decade. This is a linear graph, and this right here is the linear scale of the current. So each one of these is semi-log. We'll learn how to do all that. We're going to learn how to set up the AC simulation to simulate this from 1 hertz or 10 kilohertz to 1 gigahertz on each one of these scales. We'll learn how to do the equations and then plot our result here. So this V out dB is this right here. And we use this function. That is a function of the PTC Math CAD. Of the QUCS simulator, excuse that. And but when I was talking to you in Math CAD about the capacitor and how as we approached 1 gigahertz, this XC approached 0, making this a low pass filter. And it's comprehensive. When you can just look at this graph, you can see that we have 0 dB attenuation up to around 1 megahertz. And as we approach 1 gigahertz, this becomes 0 reactance and thus sucks all the current down to ground. And so if we would change this capacitor to where the resistor is and bring the resistor to here, we'd make a high pass filter. And then as this approaches 0, as it approached 1 gigahertz, all the voltage would be dropped across the resistor. And by controlling where the 3 dB point is, we control when we combine the low pass with the high pass, we control the bandwidth of the band pass filter, which we will see in great detail in part 2 of this video. That's it. I hope you enjoyed it, and I'm excited about getting the next video out. It's going to be really good. Thank you. Don't forget to select subscribe and hit the like button if you enjoyed this video.